In this video, we will explore the naming and properties of carboxylic acids. Note that carboxylic acids have a carbonyl group, and they have an OH attached to it. And the OH group is called hydroxyl. When you put that together, we get the term carboxyl to indicate that it's a hydroxyl group attached to a carbonyl. And they are acidic, which is where the name carboxylic acid comes from. In terms of naming, the carboxyl group will have the absolute highest priority. And we're going to number the carbon chain starting from the carboxylic acid end. And just like with aldehydes, where the aldehyde always had the carbon 1 because it was at the end of the chain, the same sort of thing is going to happen with carboxylic acid. So there is no need to indicate the carbon number for the carboxylic acid because it's always 1. The next thing we will do is end with oic acid to indicate that it's a carboxylic acid. And if it is aromatic, then the parent name is benzoic acid. And it's going to be a benzene with a carboxylic acid group on it. This is benzoic acid. All right, let's try a few. Okay, we're going to find the parent name first. We need the longest continuous carbon chain. And we always start numbering at the carboxylic acid carbon, except in aromatic cases, then you would use the aromatic carbon that's directly attached to the carboxylic acid. In the linear chain, we'll give the carboxylic acid carbon 1 and then continue to the left. So here we're prioritizing the carboxylic acid over the substituents. Then on carbon 5, we have a chloro group. And on carbons 3 and 4, we have methyl groups. So these will be called 3,4-dimethyl. And we're alphabetizing by M and C, and that will become 5-chloro, 3,4-dimethyl. And then I need the parent name. If this was just a regular alkane, we would call it hexane, since the longest chain has 6 carbons. But because it's a carboxylic acid, I will change that E ending to oic acid. And the parent name becomes hexanoic acid. And then I'll just tack that on at the end. So the full name of this molecule is 5-chloro, 3,4-dimethyl, hexanoic acid. Let's try an aromatic version. I will copy over this structure. Okay, definitely aromatic, which means the parent name will be benzoic acid. And we gave that aromatic carbon that's directly attached to the carboxylate, or the carboxylic acid, carbon 1. And then I have to decide whether to go clockwise or counterclockwise. If I go clockwise, the next substituent is on carbon 4, whereas if I go counterclockwise, the next one is on carbon 2. So I will go counterclockwise. And after that same system we've been doing a million times now, I see that there's a substituent on carbon 2, that's 2-bromo. And then there's a fluoro on carbon 4, that's 4-fluoro. And then I'll put them into alphabetical order. B is before F, and that becomes 2-bromo 4-fluoro benzoic acid. Let's try one more. Okay, long chain. And we'll always start numbering at the carboxylic acid end. So I'm actually going to go right to left here. The parent chain is 7 carbons long, so I will call it heptanoic acid. And then there are 3 methyl groups on the chain. If there are 3 of them, then we use the prefix tri, so that becomes trimethyl. And I do need to indicate where they are, and they're on carbons 5 and 6. So that will become 5,5,6 trimethyl. And then I put all of that together. So that will become 5,5,6 trimethyl heptanoic acid. Okay, in terms of properties of carboxylic acids, the name alone tells us they will be acidic, so they will react just like acids do. I would like to take a look at their solubility first. And notice that they have an OH group. So just like alcohols and just like water, this will have hydrogen bonding interactions. And the R group will definitely be nonpolar and contain dispersion interactions. Now, how nonpolar it is really depends on how long that chain is. So if that chain was 4 carbons long, that would be less nonpolar than if it was a lot of carbons. So just like with alcohols, we saw that the more OH groups we have, in this case you'll only have 1 just based on the structure of the carboxylic acid, but the shorter this R group is, the more soluble the carboxylic acid will be in water, because the hydrogen bonding interaction on the OH will be able to compensate for the nonpolar interactions in the R group. So if we call these A and B, I would consider A to be more soluble in water than B, due to the fact that there is a hydrogen bonding interaction here and fewer dispersion interactions on the R group chain. So there are some guidelines we can use here. If there are, let's say, 1 to 5 carbons in a carboxylic acid, they will be soluble in water. If there are 6 carbons, they will be slightly soluble. And if there are 7 or more carbons, then they will be insoluble, because that R group gets so long that the dispersion interactions override the hydrogen bonding interactions. Now keep in mind that carboxylic acids are weak acids, hence the term acid. And that means that they slightly dissociate in water. So if you think about this way back in the day when we talked about acetic acid, which had this kind of structure, we drew up an equation for that partial dissociation. And we said in water, it can react. We drew a reversible arrow to indicate that it's not a complete dissociation, it's a partial dissociation. And if acetic acid is behaving as an acid, that means it's donating this hydrogen to the water molecule. Well, once it does that, we're forming the hydronium ion. And that leaves the acetate as an anion, as it loses that hydrogen ion. Well, in the general chemistry portion, we just left it this way. We had the molecular formulas and we left it that way. But now that we know a little bit of organic, we can actually draw what these structures look like and see which exact hydrogen it is that is coming off of that structure. So I'm going to redraw this. This is the structure of acetic acid. If we were to draw in the carbon bonds, it will react with water and do a partial dissociation, which means that not 100% of the molecules are actually dissociating. So let's say if we had 100 molecules, maybe 5 of them dissociate. And I'm making these numbers up. It wouldn't necessarily be exactly 5, but the idea is that not all of them would undergo the dissociation process. This is actually the acidic hydrogen. This is the one that's being donated to water to form the hydronium ion. And then the acetate ion that is left behind looks like this.